Welcome back. This is our class on communication and navigation systems. So we're on the navigation portion of it. This discussion is going to be ADF, VOR, DME. This is kind of in a category of navigation that is ground assisted. There's something on the ground that will usually transmit a signal, and it can be interpreted by the aircraft systems. Sometimes they'll refer to these as dependent navigation systems. The instrument landing system is very similar, but I treat that a little bit in a category of its own, but it falls into this. It is navigation based on signals from the ground. So let's get into this a little bit. First, a little history. Originally, you can see there's an antenna posted above the cockpit on this aircraft. The early navigation aids was the radio direction finder. I'm not sure if, basically, I think it was discovered a little bit more by accident when they're listening to a broadcast. They would notice that depending on the orientation of the aircraft, you could either get a strong or no signal. So it's when the loop of so they basically use that and incorporated it so that you do not have to be going in one direction. It's got a loop of wire. The radio is tuned to a low or medium frequency station. The volume would change with the heading of the airplane. The volume was lowest when the plane was headed directly towards or away from the station, and loudest when the wings were pointed towards the station. So the only way to determine whether or not the low volume was because the station is ahead of you or behind you was to basically carefully note whether or not the volume increased or decreased as you flew along. If the volume increased, you know you're heading towards the station. And that was which direction is the radio signal coming from? And it certainly does look like a loop antenna to me. So instead of radio direction finder, we move into an automatic direction finder. Also very similar. Instead of a broadcast radio station or a radio signal, you can see in the middle there's a beacon, a non-directional beacon, a beacon that sends a signal out in all directions. A station, non-directional beacon, and you can basically see the instrument continues to point towards the station, no matter where the aircraft is. So a little bit more of the history, I guess. During World War II, the popular rotating loop automatic direction finder was perfected, and it continues in use today. So the loop actually rotated, so the plane didn't have to. But it was a popular way of doing it. When the automatic direction finder, or sometimes we'll refer to it as airborne direction finder, finding. And again, when it's tuned to a low or medium frequency non-directional radio beacon or to an AM commercial broadcast station, the needle on the ADF indicator points to the station's transmitting antenna regardless of the heading or the position of the aircraft. So you don't really have to have a rotating loop. But we'll find you still do need a loop. This figure illustrates the typical equipment that makes up the automatic direction finder system. There's a receiver, a loop and sense antenna. The sense basically helps you to see whether you're coming or going. And 3 variations of ADF bearing indicators. So you can have one or more of these indicators that all play off the ADF signal. A fixed card indicator, a movable card indicator, or a radio magnetic indicator. A little explanation of how the loop and the sense antennas work. The loop antenna, you can pretty much see it in the green. It's got a post on either end, and it looks like the main transmission is from where it goes from the housing to the post, and you can see there's 2 counter direction signals, like moving like a gear would. So the loop antenna is highly directional, and the maximum strength received when the antenna is pointing either directly towards or away from the transmitting antenna. And then there's a sensing antenna, basically that receives equal strength from all directions. So it's a combination of a highly directional and an omnidirectional antenna. You put them together and you get this type of field. Sometimes I guess they'll refer to it as a null field. And you might have to read that. Just be aware, ADF, loop, and sense. Again, here's our loop antennas showing you, yes, when you're equivalent to your wings, you get a strong signal. But when you're equivalent to the nose of the aircraft, you're not really getting much of a signal. I guess that's what they're trying to show us there. A block diagram. I guess this is a simplified version of the rotating loop antenna. Well, we can definitely see our antenna and our indicator, and the receiver does more than just receive. It amplifies, it mixes, it detects, demodulates, and also amplifies enough so that a speaker can be driven. And did I mention there's a filter in there also? An oscillator to basically keep the timing correct. A loop and a sense antenna are both tied in to the unit through their own radio frequency amplifier. That was the rotating loop. The fixed loop, it's changed very little over the years, but the hardware has changed dramatically to keep up with the state of the art. Modern high-speed aircraft do not use an actual long wire sense antenna, but part of the structure is made to function the same way as the long wire. Alright, so they're showing the fixed loop over here on the left. A goniometer. Part of the ADF system used on aircraft includes, so what is part of the system? There was a receiver, there was an antenna. Oh, it's the type of antenna. There's the three different options of antenna. RMI indicator, marker beacon antenna. Those, are based on somewhat reality, but what are they really looking for? The sense and loop, or loop and sense antennas. C. And we already went into the details of those antennas. One antenna can be used for the radio range and the standard broadcast bands in light aircraft because when can you just use one antenna to do more than one function? A, because the two ranges are close together. B, because the antenna is omnidirectional. Or C, the antenna length may be electronically adjusted. So, close together, what does that mean when that certainly would look like that would be close enough? I guess there's no good way of explaining that, just by going over the question. They are close together. If you're actually studying it to the detail that we might study it, they don't seem that close together. Well, one's in the low frequency range and the other's in the medium frequency range, but those are actually close enough together that one antenna can work that. I'm not exactly sure how, but I've got an idea. Normally, antennas are sized to the size of the wave coming in. So low frequency and a medium frequency wave come at different sizes. But I think in other parts, like the VHF common nav, that makes a little more sense. As a matter of fact, we even know that broadcast FM ends at 108. The next 10 is for navigation, and then the next 20 are for communication. So those are real close together. As a matter of fact, two of them might be almost sharing the same 118 point something. But they're talking here in theoretically, and I don't know, maybe they didn't place this question appropriately. After an automatic direction finding antenna has been installed, what do you do once you install it? The antenna, that is. Test it to see if it works, I would presume. Let me see. A, the antenna must be grounded. B, the loop must be calibrated. Or C, the transceiver must be compensated. All right, I think if you know about the loop and sense antennas, I think you're already kind of zeroed in on it. Loop looks like you actually are picking the correct word for an ADF question. So the loop must be calibrated, which is a true statement of itself. Most all antennas must be calibrated. So you do that to check for quadrantal error. That's the error caused by the metal in the aircraft structure, distorting the electromagnetic field of the received signal, similar to our issues that we had with compasses back in instruments. They would call that, what was that, deviation? And variation was the difference between the two poles. Yes, deviation. So this, for ADF equipment, we're calling it quadrantal error. All right, there's some detail there for you physics engineers. Azimuth inaccuracy, which are greatest between the four cardinal points with respect to the center line of the aircraft. Technicians, don't worry about that. Apparently, it's required by regulation anyway. So there's a regulation that says after completing the installation of an ADF antenna, it's essential that the loop be calibrated, and they even show you in the AC how to do it. What does the term ADF stand for? Sometimes all these terms get you mixed up, but that one is direction. If you can get the word direction in there, I think you're fine. The A and the F, that changes a little bit. I don't even want to say the other word because you'll start thinking of that word. But it's either direction or something else. But in this case, it's direction. Automatic direction finder is, I think, the most common way to say it. But this answer here started with airborne direction finding. I think you're almost better off with the part that I added there. Or to be on the safe side, say both. VOR, that stands for VHF, or Very High Frequency Omnidirectional Range Navigation System. So you can kind of see where the VOR comes from. VHF, Omnidirectional Range. It is a navigation system. It's similar to finding your direction to a broadcasting signal. In effect, it's broadcasting a signal in a circular fashion. So, without getting too technical, maybe that's using a lot of directional antennas in such an array that they're actually working as an omnidirectional. One nice thing about that is when you pick up the signal, you can pick up a slightly different signal depending on your orientation to the broadcasting signals, which is in effect the basis of how the system works. You can certainly look at that with much more detail. There's an example of one. They all have certain similar characteristics, but the construction methods vary widely. This came after World War II. The forerunner of the present FAA they realized that they needed some navigation set up. I mean, early navigation may have just been somebody lighting bonfires or holding torches. Not that effective. Aircraft approaching or departing from a busy airport should be able to use more than 4 courses. Also, the system should not operate in the low frequency band, because it's susceptible to all types of atmospheric interference. I don't know if that's telling us much about the system. This tells us a little bit more. You can in effect see that it is sending the signal out in a number of transmissions. VOR station, such as one pictured, transmits 360 radials in 1 degree increments. Since there's 360 degrees in a circle, it broadcasts at all 360 points. So you can really get a precise reading of where you are in relation to the station. They are also numbered clockwise, so nothing too fancy there. Same direction as a standard clock. This is an overview. You certainly have readings available to you from the textbook, which we provide portions, but I don't believe we're going to be providing much more than what you're seeing on the screen here. And there's a lot more information in your textbook. What type of antenna you can see on the vertical stabilizer and the rear empennage of the aircraft, and you can see it here also. You can see two different types. This one looks like a towel handle, and this one here looks like whiskers, I guess. So they call it a V dipole. It's horizontally polarized, or the more modern towel rack. That works as an effective horizontal dipole antenna. A little look at the guts of a VOR antenna. It may contain a device called a balloon, and this is an illustration of what that would be. It's located at the antenna end of the coax cable for more efficient transfer of energy from the antenna to the coax and receiver. Jet carrier jets use a VOR antenna that's mounted inside the vertical fin with non-metallic flush covers on each side, so you cannot even see it, but it's under a composite cover, not a metal cover. The VOR equipment, again, like we looked at DME, it's very similar. There's an antenna, various types. There's a, this is kind of one of our main navigation. You can see we talked about COM on one side of the receiver. Well, it basically shares the other side of the receiver. And look where it's actually tuned to. Look how close those frequencies are. Communication channel started at 118, but but you can use navigation right up to a 117.9, so that's a good indication of where the bands do change. So navigation has the 10 between FM broadcast and aircraft communication. There's a nice indication of a VOR indicator. You notice it has a to and a from flag. Because which way is the station? Well, it's that away, but are you going towards it or away from it? In this case, it looks like the from flag is visible. Pilots will learn how to use this equipment. They locate a station on the aeronautical chart, which is the map, or some other reference, which is the internet, and determine the frequency that's being broadcast by that particular VOR station. Then you tune to that frequency, you listen for the Morse code type identifier to verify that you have the right station, and then so as you might have seen, VOR stations do transmit a Morse code. Apparently it's a 3-letter identifier. Probably close to their airport. I would presume Miami would probably be MIA. Just a guess. When the station has been identified, the pilot is ready to use it for navigation by means of the appropriate flight deck bearing indicator. Modern airliner flight management systems automatically decode the Morse code signal and present the pilot with the alphabetic station identifier automatically on the screen, I'm sure. What is the function of VOR equipment? Instead of talking for a half hour on this, why not just one word? Is it communication? No. It's navigation. And of course, when I convert these into multiple choice questions, you could probably bet communication is going to be one of the options. And then what's the third one? Landing? No, the answer is navigation. Name the components of a typical airborne VOR navigation system. Airborne means what's in the plane, not what's on the ground. So don't start describing the little structure that we've been showing you pictures of. They want to know what are the components of the system. Well, basically, we saw the antenna. There was the receiving unit. Our example, it was actually in the same unit occupying the right side of the ComNav unit. And then what else was there? A indicator. And I imagine there is a you can get into describing the guts of the receiver. I don't think they want that much detail. A receiver antenna's frequency selector and a visual display indicator. So the only one I really missed was the frequency selector. So basically it's the dial on the radio to get the VOR station's broadcast signal. The preferred location of a VOR antenna on light aircraft is where? Is it at the bottom of the fuselage and as far forward as possible? Or is it at the top of the cabin with the apex of the V pointing forward? Yeah, that's a lot of detail there, and it does look like one of our pictures, so far I like that. Or C, on the top of the vertical stabilizer. Well, I like that also. I might like that better than B. It is light aircraft. Let's see what the official answer is. But I'd say there's a bit of an argument for B and C. Top of the vertical stabilizer sounds best, so. Ooh. Top of the cabin. Yeah, so at the apex of the V pointing forward. It's been a while, but that's probably why I like the answer. But usually if I write a question, I'm not going to write it like that. I'm going to dance around this. I'm going to say on top of the horizontal stabilizer or something. All right, be aware. Top of the cabin. It's mostly the apex of the V pointing forward. Remember that as being part of the right answer. Okay, nothing too fancy with the second explanation. All right, now we're moving into our next area. All right, distance measuring equipment. So VOR gives the pilot the direction to the station, but it doesn't really tell you how far away the station is. Well, there's a way to combine that with DME, which is distance measuring equipment. So you already know the direction, now you want to know the distance, and you have another system, which could be a part of the VOR system, that indicates the distance. It's also from the broadcast that you get from the station, but you also have to factor in the elevation of the aircraft to be able to see how far you actually are as far as ground miles, as opposed to a direct line, like a laser line, from where you're at, which might actually be longer, as you can see in the example, and the higher you are in elevation. Okay, and an independent DME broadcaster on the ground. It's not as fancy as VOR. You could see that right there. It doesn't have to worry about direction, so omnidirectional. Anyone? It's more for distance. You can see, I like the illustration, the wiring diagrams of the antenna and the indicator, and even the analog indicator, which actually converts us into the mileage. The distance measuring equipment is often combined with the VOR. Um, and the military version of the VOR is the VORTAC, which is a combination of VOR and TACAN, and that provides distance information also. But it's a military application, so a VORTAC gives them distance and direction. But for civilians, we get the same with VOR/DME. And you can even see it if you flip through the channels, even on the in-flight entertainment systems. They'll usually give you this type of information. It'll tell you what your ground speed is, how long it is until landing, and how many miles. So it gives you a little bit of a calculation from distance and direction. It consists of equipment here. What do we have? We have an indicator, or I guess the indicator is part of the receiver transceiver. And the antenna looks like a little shark fin on the underbelly of the aircraft. All right, so there's not much to the system components. So therefore, they probably will not ask you what are the components of a DME system. Slant range, you can kind of see that is unique to DME equipment. So if they're prone to ask you something, it's so you understand this concept a little bit. If you're a mile up in the air and you're actually a mile away from the station, what is the actual reading? Well, it's what is that? The hypotenuse of a triangle. This is a right triangle, so the third side. Trigonometry review will throw that out, but you can see if it's one up one side, the third angle is actually 1.4. You might use that formula for calculating simple trigonometry questions. Maybe not. Let me see where I'm at. I was getting a bit of an echo chamber in here, so I put this where's my head? This muffling material behind me. I'm going to have to dress it up though. Already I've made a few improvements here of my screen capture. I was cutting off parts of it, so going forward you might notice that the screen is a little more lined up. The audio is getting better, so making some progress there. 10 videos from now, I'm sure I'll progress further, hopefully. Production notes. All right, so DME has those bottom on the underbelly mounted, mostly little shark fins, although we see a ball and post also. Depends on the aerodynamics. I imagine the higher performance aircraft would use the other type, the white type. The DME antenna should be located in a position on the aircraft that will A, not be blanked by the wing when the aircraft is banked. That's always a good answer. That is one of the major concerns with antennas. So unless something else really jumps out specifically, I would say that that's a good rule of thumb, almost period. B, permit interruptions in DME operation. I'm not exactly sure why you would want to do that. C, eliminate the possibility of the DME locking on a station. Well, you're not going to do that with an antenna locating. locating an antenna. So yes, it's installing an antenna. The only concern you'd really have is to make sure that it's in a position so the wings aren't going to block it off. So maybe it is located further aft, if depending on where the fuselage allows, or maybe all the way forward. I'd probably say further aft. Yes, so it's not blanked by the wing when the aircraft is banked. They don't really suggest anything. I would imagine that type of suggestion, it comes with the equipment. All right, which of these antennas is a typical DME antenna? Since number one looks like it is installed on the bottom of the fuselage, and it is a fin type antenna, I like that the best. We might remember that. We probably don't. We haven't done ILS much, but number two is the glide slope. Number three is the VOR. And number four looks like a regular communications VHF communication antenna. Let's see how we're doing. It is number one. Do we get the answer of all? Yes. Number one is DME, or it's also used as radar beacon transponder. You're communicating to ATF. You certainly want one on the bottom, and it looks very similar to that, so it could be the one right next to it. Glide slope, C, VOR, and localizer. Normally they're in one. And 4 is the VHF communications antenna. We'll get into glide slope and localizer more in the instrument landing portion, but you're already getting a little preview as to their antennas. What does DME stand for? Do we have the same issue that we did with ADF? I don't believe so. But you could. The person asking you technically is the designated mechanic examiner for the FAA. So technically, the DME is asking you, what does DME stand for? Well, he's not asking for that. He's asking for distance measuring equipment. Or she. Ironic. Where on the aircraft would you expect to find a DME antenna? On the bottom of the fuselage, in a position so that it's not blanked by banks, blanked by the wings when the aircraft goes into a bank. I think I could probably think of a better way of saying that, but let's see what this one says. Generally on the bottom of the fuselage in a location that isn't blocked by the wing during turns. Oh yeah, much cleaner way of saying that. Okay, and when installing a DME antenna, it should be aligned with the A, null position, B, angle of incidence, or C, center line of the airplane. At this point, what are you most familiar with? The center line of the airplane. You know that's where it's going to go, on the bottom of the aircraft. So you don't have to worry about the other technical references. Center line of the airplane should be fine. On the belly. So that it runs parallel with the center line. So I think there's several ways of saying that. So parallel, in other words, you're not going to put it flat against the airstream. So yes, you're going to run it parallel. I see what they mean. That's a good point. You could throw that in. Somebody might go out there and I'm just going to screw it on. Well, let's make it, you know, straight. All right, is that it? I guess so. All right. Well, I appreciate you joining me, and I'll see you on the next one. Goodbye.